Welcome back to the Quant Trading Room YouTube page. In today's video, we are going to go over structural entropy and how coding might be used so you can use structural entropy in the financial market. If you'd like an in-depth breakdown of the exact process, I'll link our Medium article below in the comments. This video is more so you can get Python code of how you might gather and interpret the entropy values themselves. I've already gone ahead and imported all of the packages that we'll be needing. We actually won't be needing these. We start with pandas and numpy for data frame and array work. Yfinance is used to import our index data with the dates and closing prices and everything like that. Matplotlib and Seaborn is for graphing and visualization. Datetime is so we can index everything correctly, and TQDM is more of a coding structure so you can visualize a progression bar. So we are going to start by selecting a small sample of stocks and indexes. So index selection. So this is just going to be a list of a few different indexes that we can use to pull from Yfinance. So you can go ahead and go on Yfinance's site and pick out whatever stocks or indexes or really any assets that you feel like you want to kind of analyze. So I believe we have 10 here. Excuse me, ZW. So you can add as many as you want. You can pull the data from wherever you want really as well. But we are doing Yfinance out of ease of use. So there are our 10 contracts. Now we're going to set up a data frame and grab the data from the Yfinance package. So we just basically set up a blank data frame, and then for contract in contracts list, oops, I guess it already indexes. We are going to download yf.download each contract. We are pulling in 1 hour intervals, and we are doing it over a period of 6 months. Like I said, you can gather this data however you want in whatever fashion you want, but for the purpose of the article, we're going to stick to those as well. And then we are going to index on the index on the name, and then we are going to append the download. Okay, so that should take care of all of our stocks, and just so we can kind of visualize what's going on here, we'll go ahead and run this cell. Oops. Oops. Apparently I can't spell. And I can't correctly put 1 hour. Okay, so there we go. Oops. Sorry, this meant to be DL stock, so it gets in the data frame. Okay, there we go. So as you can see, we pulled all of the contracts in our list up here, and it gives us the open, high, low, close, the adjusted volume, adjusted close, volume, and stock. And it gives us to it every hour. Sorry, I had to double check. Yes, every hour. So this is only the first 5, but if you wanted to view the whole data frame, it would be pretty long. Okay, so here we are. We're going to reformat the data so that is in a usable format for us. Index. So we are going to set the timestamp series to the index, and then we are going to sort the values based on two different categories here, the stock and the timestamp, and it will be in place. And then the second thing we're going to do is we're going to make a copy of that time frame, or sorry, of that data frame, but use a different index here. Timestamp. And unstack it. And then here we are just going to visualize again what we did here. Okay, so as you can see, we are printing the df close now. So the closed values from up here are now in the data frame, and it is sorted on stock as well as time frame. So each of these is going to be, each of these columns is going to be 1 hour's worth of time. All right, next steps, we are going to make the data frame log returns. So then we can see the percentages. So percent change on the first axis, and then we're going to apply NP log, and we'll show what that means here. So basically, we are just applying a log to the adjusted returns from up here. So it is taking the returns as a percent of the previous timestamp. So obviously the first hour won't have anything because it can't be compared to the hour before that. But each of these are a progressive log return against the previous series. All right, next step is we're going to just get a visualization of the data here, and this is more just for our visualization purposes. Title. And we can make this, what do we want this? 18 by 10 maybe? Is that going to be large enough? Great. So here we can just get a visualization of our log returns and the frequency at which it happens. And as you can see, most of them fall right about on the 0% log returns. Next steps, we are going to get a visualization for the correlation between each of these. So we'll use a correlation cluster map from the Seaborn package. So here you go. This is the cluster map for the 10 different indexes that we drew. So clearly right down the middle, they should be equal, but you can see the distribution here. Now, in order to use structural entropy, we'll need to do continuous monitoring in the market, and this means generating a sliding window of the time series into subperiods the size of our sliding window. So for our purposes, we're going to make that window 48, so 48 hours. And then I also have here some just visualization tools. This isn't part of the 6-step process, but this is more for a visualization. Oops. I'm gonna uppercase this. This is more for visualization purposes of the log returns. So this is the sliding average of log returns and the sliding standard deviation. Alright, so this next part is going to be the functions that will generate the entropy value for each sliding window period. So if you're following along in the article, this is the, in the applying the sauce sections, this is the functions that will be used for the 6 steps in constructing the structural entropy. So first we're going to make the correlation matrix. So get correlation matrix, and for that we need the data frame, the start and the end time periods. So oops, the sequence goes. So the sequence is going to be the data frame from the start to the end dot t, so it flips it. And the correlation is going to be the sequence correlation values. Oops. And we want to return those values. The next step is actually getting the structural entropy. So there are several different functions in here. And for our purposes, as you'll learn later on, for the adjacency matrix, which is step 3, we are going to program in a threshold, and then this way you can change whatever threshold you need. There, and you can change the sequence length as well. Oops. Okay, so the structural entropy will start with a dictionary that holds the timestamp for the entropy values as well as the entropy values themselves. And then here we'll make the sliding window. So for I in range of the sequence length, followed by the df shape. So this will basically do each of the steps for as many sliding windows as there are for the length of the data frame. So this is the sliding window part. So this is basically step 1 and 6 combined. So the first step is getting the correlation matrix, which for us is going to be step 2. So get correlation matrix, step 2. Oops, I should make these 1 and 6. Okay. So correlation matrix equals get cormat, and this is going to be for our I minus sequence length. By I steps. Sequence length. I misspelled that there. Length. I spelled that there wrong too. Okay. Sorry, this should be backed up 1. And so should this. The second thing we're going to do is get the adjacency matrix, which would be step 3. And this is the threshold as well. So for this one, so if the absolute values from the correlation matrix that we just figured out are above the threshold that you're putting in here, you are going to basically add them in the next step. So as type integer, this is going to get the number of connected components, which is step 4. Community detection, basically. Sorry, I should make that more clear. There you go. Connect components, correlation. So there's that. Next step is looking for the unique components so you can identify the probability matrix. And so if you're following along in the article, this is going to be part 5A. Actually, all this stuff is going to be 5. Excuse me. Look for unique components and counts to the number of components divided by the total number of nodes. So no matter how many communities there are, you're going to divide by the total number of nodes, which in our case is 10. Count equals unique labels. Return counts equals true. And then you're going to apply that to get the probability vector. Count divided by count.sum. And this is going to be 5b here, entropy value. Step 5b. B equals. So this is the large summation formula that's in the picture. So negative probability, excuse me, probability vector times the log squared of p. And then you basically just add it to the dictionary that we created up above. And you're just going to apply the df columns for this particular window for the timestamp. And then for the entropy value, you'll apply the entropy value, obviously. Okay. Maybe I should make this more clear. There we go. Alright, let's run that to make sure everything's okay. Good. I did realize I couldn't spell here, so this is supposed to say structural entropy. I initially missed this R, so. Next up we are going to do is we are going to give a graph of what the different thresholds look like, mapped against the S&P 500 closing prices from Yahoo Finance. So won't bore you guys with me typing everything out, but essentially we're just getting thresholds from 0.1 to 1 in steps of 0.1, and then we're going to make two subplot rows of figure sizes 18 by 10. And then for each threshold, so 0.1, 0.2, 0.3, all the way up to 0.9, we're going to generate a structural entropy data frame. And this is just taking the same log return data frame from above, our 48 subperiod window that we marked above, and the threshold for all those different variables, and it is going to plot them in a graph. And then also on this same graph, we're going to download the EES, which is the S&P 500 index or future in 1 hour intervals for a 6-month period for the same 6-month period, and plot that as well. So we have all those different thresholds up on top, and the graph of the S&P 500 close at the bottom. So this is a bit of a jumbled mess, but you can kind of see how different thresholds might compare against the S&P 500. So if we wanted to, get use of how we might use structural entropy, we would want to choose one of these thresholds specifically and try to derive some information from that. So technically all that above was the 6 steps. So I am just going to explain down at the bottom of the paper what kind of information you can derive from the thresholds. So in the paper, what I ended up doing was using our threshold of 0.6 against the median standard deviation of our data frame data from above. So here's what that looks like in code. So the entropy is going to be in red, with the rolling window of median standard deviation in blue here. So as you can kind of see, they have inverse relationships. So you can take that how you will, and you'd have to figure out how you want to format a trade around that. But you can clearly see, when the entropy values are low, the median standard deviation of our log returns is pretty high, and vice versa. So that is just one of the infinitely many ways you can make a comparison. You can take any of these thresholds against any meaningful value from the S&P 500 and probably find some correlation, and make some pretty useful trades. So that is going to conclude our structural entropy topic. Feel free to leave a comment or message us with any questions. Again, if you need a more in-depth breakdown, go read our Medium post, which will be posted below. But thanks for tuning in to the Quant Trading Room, and we look forward to teaching you more about different trading strategies in the future. Thanks.